All right, thank you all for coming out today. So this talk is going to be about the testing and emulation environment within Zephyr and how we can accelerate code coverage with something that I'm calling the generic test coupled with emulator backend APIs. So we're going to start off with a quick overview of what the Zephyr emulation system is like, then introduce the generic test and backend emulator API, and then we're going to do sort of a walkthrough of an implementation of that, just so that we can all get very familiar with how to do that, and hopefully we can maybe try that ourselves with a particular sensor or driver that we like to use. So a little bit about myself first. So I'm a firmware engineer at Google working on Chrome OS. So my team does the embedded controller for Chromebook devices. So we're sort of a system management microcontroller that lives on the device and is responsible for managing things like charging, keyboards, sensors, USB power delivery stack, sort of these low-level functionality things in the Chromebook. And we're actually an open source project, so you can feel free to check us out, look at their code. And then over in the public Zephyr world, I contribute to the Zephyr sensor system, and also have worked on testing and Twister. So if you submit a PR to the sensor drivers, there's a good chance I might be one of your reviewers. All right, so let's go ahead and start off with Zephyr emulators. All right, so when we're talking about emulators in this context, we're not exactly going into things like QEMU or hardware emulation. The best description I have for what a Zephyr emulator is would be more like a mock peripheral. So obviously, your embedded application is going to be interacting with a lot of things like GPIO, EDCs, I2C buses. But if you want to be able to compile and test your application on a host PC, obviously we're going to need to substitute that kind of hardware in with something else because it wouldn't be available otherwise. And so Zephyr has this concept of emulators that can stand in for these devices. They are coded in C, and you'd be normally using these in a native POSIX, native SIM test environment. So you can piece together sort of a replica of your hardware in the device tree for your test using these pieces. And it's super powerful for validating your application without having to use real hardware. It's a lot faster to iterate through, and you can also run it in your CI, so you can get automatic regression testing and make sure that nothing you're doing is accidentally breaking something. So the sort of flow when you're doing this is that you would have unit test code up top, and this would be calling into the normal Zephyr APIs. So we're going to focus on sensors today, so we'll call into the sensor API. That interacts with whatever driver that you want to be testing. And then that sensor driver is doing I2C operations, but instead of going out to a chip I2C driver, it's actually talking to a sort of a virtual I2C bus, the I2C emul. And that in turn is talking to a virtual sensor emulator. And so those two parts, the driver under test and the emulator, are kind of what are working together to power that unit test. And the role of the emulator here is basically act like the chip. So it accepts I2C operations, it has an internal register store, can return data that's being read to it, basically act the same way that a normal sensor would. So a lot of the things I'm going to talk about today are applicable to other classes of devices, but for the sake of this talk, we're going to be focusing mostly on these sensor emulators specifically. So if I haven't mentioned already, the testing and emulation is a good thing. So we, of course, want to provide our users with the most stable and bug-free code possible, right? And so unfortunately, we do sometimes have run into issues with the sensor drivers, right? And so as a reviewer, I do get to see kind of what kind of bug fixes come through from time to time. And one of the common categories of bugs are things that have to do with sort of range problems on sensors, and also unutilized features. I don't want to call out particular sensors or PRs in this talk, but One kind of problem, just to give you an idea that kind of happens a lot, is somebody will develop a driver for, let's say, a temperature sensor and commit that upstream. And maybe they were using it in like a room setting like this, testing a pretty narrow range of temperatures. And it works perfectly for that application. But when somebody else comes along later down the road, and they want to use this temperature sensor in, like, say, a freezer or a weather station or something where it's being exposed to a much broader range, they'll find that the driver crashes because it's never actually seen a negative number before, or something like this, right? I have also in one case seen a situation where a sensor purported to support operation on I2C and SPI, had dual bus feature. But if you initialize it in the SPI mode, it would actually immediately segfault. And so I might have actually been the first person to run that code, but it was in the tree. And so I think issues like this are an opportunity for improvement. And I think that the emulation and testing combination is a really, really good way to thoroughly test these drivers, work all the different features, get good code coverage, all the branches, and then be able to ship a driver that we are pretty confident in and stable. Now, of course, there's some time investment involved here. And so part of this talk is going to be to propose a system that makes this a little bit easier. But I do think overall that it is worth it. So when we're talking about a typical sensor plus emulator test, this kind of mirrors the slides we were looking at earlier. But we have that test code, right, calling sensor API functionality. So it hits the driver. Driver is doing its I2C operations like normal, talking to this emulated sensor. Now, in order to close the loop right here, the test also has to be able to control the emulator, basically set expected values, expected state, so that when we talk to it through the driver, we can actually make sure that it did the thing that we wanted it to. So how does that work? Typically, these emulators will expose some kind of custom API to allow you to configure it into a particular state. So you might have a function like this, where we say set register hex 45 to that ugly hexadecimal number. That would, in this case, be encoding some kind of temperature reading in the native register encoding that driver uses, which is non-standard almost all the time. We then call the API to get a sample using fetch, get, or whatever. And then we just compare that what we got out from the driver is what we programmed into the emulator to begin with. And so this works pretty well. This basically tests the data path of the sensor. But if you do this a lot, you'll suddenly notice that this one part right here is kind of the only step that's unique to a device, right? If you could have a standardized way of talking to these emulators and let the emulator be in charge of doing that conversion from like a real world SI number into a register representation, then the test could suddenly be like reusable. And that's what we're going to explore in the remainder of this talk. So step one, let's standardize an API to talk to these emulators and basically configure them for testing. So one of the important points that we want to emphasize here is that we should not be exposing any kind of implementation details about how the sensor represents a particular reading, right? We saw earlier that a lot of times these sensors will just have strange counts for how they represent temperatures and other readings. It could be in like weird units like 1/8 of a degree. We definitely don't want to have to be dealing with that. And so if we can basically make the emulator responsible for accepting a real world value and it being the expert on the chip that it's emulating, map that into whatever it needs to do, then that would make the test side a lot easier. And finally, if we can add some kind of discoverability mechanism to the emulator, such that we can learn from the emulator what channels and what their respective ranges are, then we can really have a generic test coupled with this that's able to basically test a chip without knowing anything about it, only what it learns through the emulator. So I should mention that the concept of the backend emulator API is not completely new in Zephyr. There are some other classes of device that have been doing this. But I think it's particularly important that we bring this to the sensors world just because there's such a huge variety of sensors out there. There are dozens, probably over 100 drivers that are in use. And so I think that's a high impact area to deploy this. So let's dive into what this API actually looks like. And so this is going to be the point where I walk up to the screen and like point out some things, but unfortunately it's like 20 feet tall. So the main function is set channel, all right? So given a channel enum, and this could be something like ambient temp, XL, XYZ, there's a list of them in Zephyr if you want to take a look. So given a channel enum, set the particular value on an emulator, and then the emulator should do whatever it needs to do internally to make sure that the next read from that channel returns a given value. And then we also have the associated getSampleRange function, which is what we use for that discoverability mechanism. That's able to, if a channel is supported, basically return an upper and lower bound, so we know what to basically test with. And also an epsilon value, which sort of is like a tolerance. And that basically encodes the bit depth or sample resolution of that sensor, just so that we're not trying to expect an output that's tighter than the sensor can actually provide, We have since expanded this to also talk about sensor attributes, although this is still up and coming, so we're not going to focus on that too much, but just wanted to call that out in case you go look at the API, which is, by the way, in emulsensor.h if you want to follow along in the code. All right, so that takes care of the emulator side. Let's go on to the generic test. So I have a wonderful flowchart about how we can step through that process and how it can work. So first thing we need to do is detect if the emulator in question actually supports the backend API. If it doesn't, we're obviously just going to skip that. But if so, we can start that channel discovery routine where we're going to iterate through all the different channel types that Zephyr supports. And if we don't get an error code back from this function, we will basically store that channel information, the ranges, in a table inside the test. And from there, we can go ahead and interpolate some test values. So obviously, we're going to be using the absolute minimum and absolute maximum that the sensor supports. But then by default, we also pick a total of 5, so 3 additional points that are linearly interspersed along the sensor's range. That's configurable if you want to do something else. But we store those values, and then basically we can, one at a time, go through, set those on the emulator, and it will do whatever it needs to do to update its internal state, convert from a real-world SI unit. Everything in the generic test is using real-world units, such that when we read it back, we get that expected value returned from the sensor driver that we are testing. And then we can just do a simple comparison. Are we in tolerance or are we not? If not, we can abort the test at that point and return some information to the user. But if we do pass, then we can continue and keep doing this for the other sets of expected values. We basically will try to do every supported channel at once, and then repeat that for each of the 5 expected values, just to do a little bit in parallel. And then finally, we can repeat this for any other sensor that we want to. So I did want to go on a little bit of a side trip here and talk about fixed point numbers and the sensors v2 framework. So if you noticed in the API that we showed a couple slides ago, the values had a type Q31T. And there was this other parameter called shift associated with them. What does that mean? So this is a representation that is being used by the newer Sensors v2 API. If you haven't heard about this before, you're probably not alone. This is sort of an experimental slash soft launch feature that's been in the works. But we think it makes sense to start adopting this for new code, such as the generic test. And one of the things that we're doing in this new API is we're no longer using the sensor value struct, where it has 2 fields basically representing integer and then milliunits that you then have to basically add together and is very difficult to do arithmetic with. So we wanted to use fixed point numbers in a 32-bit container instead. And this makes a lot of the arithmetic easier in the processing with sensor data. The rest of the sensor v2 system basically plays more nicely with Zephyr's DSP systems and enables higher throughput reads through the real-time I/O technology. There is a slide at the very end that has a link to more information about this. I just wanted to quickly mention it because you might see some references to it in the rest of this talk. But aside from that, we're going to focus mostly on the fixed point numbers here. And so I'm sure you're all familiar with how counting in binary works. But in the fixed point case, basically what we're going to do is we're going to apply fractional weights to some of the bit positions in the number, right? So we're familiar with 2's complement that you can kind of see there on the left, but we can keep extending to negative powers of 2 on the right. And so basically we can start encoding fractional numbers in binary, and you don't need a floating point unit to work with this, so it's very friendly to smaller hardware. This is really common in the DSP space, so if there's any DSP engineers out there, you probably know all this by heart. What's one of the benefits of this is that we can actually adjust the precision of this by moving around where our virtual decimal point is. All right, so if you have a sensor that's spitting out really large numbers, you can sort of trade off some of those fractional bits to have more space or more headroom on the integer side. And the location of this decimal point is sort of defined by the shift value. This is a little bit different from the Q notation that you might be familiar with from the DSP world, but it sort of implies the same thing. Next slide, I got a couple examples of what different shift values mean in terms of range. So you basically, every time you have one of these Q31 sensor values, it has to be accompanied by a shift value that communicates to whoever's consuming it where that decimal point lies and what the actual range of the number is. But this is flexible and allows you to basically get the best precision that works for your sensor. So a couple examples are out here on the board. 0, shift to 0 basically means that you have a -1 to just shy of 1 range to work with, all the way up to 31, in which case you have 0 fractional bits and it's just an int 32. So just to do a quick example, since being able to work with this is important if you want to use the backend API. If you had a temperature sensor that has a range of -10 to 100, what would be the appropriate shift value to use with that? Well, the answer would be 7, because that would give us a range of -128 to just shy of 128. That fits our range. That's the smallest shift that fits our range. So that's what we would use. And if you wanted to convert back and forth, there's a billion ways to represent this arithmetic, but you're basically just doing a rescaling. This one makes it very clear how the shift is incorporated. And that is how the temperature value of 50 degrees would look like in hex in memory. If there were decimal places to that number, you would see more bits being set in the lower significant bits. One thing to be mindful of when you're working with this is it is possible to overflow pretty quickly since you're dealing with some larger numbers here. So you might have to use an N64 container temporarily while you're doing the arithmetic. And you want to order your operations carefully to make sure that you don't have any rounding issues if you lose precision by doing too many divides, for example. But this will make more sense once you start working with this and can study some code. It is a little bit of a learning curve, but you will get used to it. All right, so for the last part, we're going to basically take a tour of a particular implementation. We'll take a look at the generic test as it lives right now. It is actually live within Zephyr right now, and there are about, I believe, 3 or maybe 4 sensors that are using this mechanism. We're going to take a look at the AKM09918C digital compass, because that's something we had on the dev board that was lying around. So that's been one of our sort of test sensors to work with. So first thing we're going to do is add a backend API implementation to the emulator for this part. And so as a prerequisite here, we're going to assume that we already do have an emulator for this part. That is something you have to set up first. But that's actually honestly not too challenging because a lot of these devices work pretty similarly under the hood. And so you can, with a little bit of copying and pasting, put something together in not too much time. But the first thing we're going to implement here is that getSampleRange function that we talked about earlier. This is a pretty simple sensor. It supports the channels that we have laid out right here. It's a magnetometer, so 3-axis. Each axis has the exact same range. It's plus minus 49.12 Gs. And so that number means that we want to use a shift of 6, plus minus 64. So we're basically going to return shift of 6. We're going to compute the upper range based on that formula we looked at in the other slides. We can copy it over for lower. And then the epsilon, in this case, is basically based on the value of one least significant bit in the register of the chip. All right, so that's basically our precision. I recommend sometimes scaling it up by like 1.5 or so, just to give you a little bit of headroom when there might be rounding errors in other parts of the code. But basically what we're saying here is that you're never going to see a step smaller than that figure. If the caller is requesting a channel that is not one of the 3 above, we basically return E not supported. We do not use the triplet samples. So there is a magnetometer XYZ single channel, but for simplicity, we just handle them each separately. All right, so let's take a look at the other function that we implement. This is the one that actually sets the channel. This is only half of it. So we just do some input validation to start off, make sure that we're only accepting values for channels that we support. So once again, we'll see the magnetometer X, Y, and Z. Otherwise, we return an error. And then we're basically just going to do some of that math in reverse so that we can convert that real-world SI unit number into whatever register representation this chip actually needs. And so as you can see below, we're basically going to convert this down to a 16-bit value that we can shove into our register store. All emulators have some concept of representing the registers that are on chip internally. In this case, there's just an array called reg, probably of size int 8. And we basically put the upper and lower half of the reading into it. One other thing that we have to do at this point is set the basically data ready bit at the top right there. This particular chip has a bit in a status register that gets set whenever a new reading is available. The driver will actually refuse to read any samples if that bit is not set. So we have to set it here. We are an emulator, so we have to behave like the real chip in order to make the driver work correctly. We're also clamping the value down just in case somebody sends in something that's way higher than the chip actually supports. We don't want to allow invalid register writes to take place, so we do a clamp. But long story short, you give this a value in Gs, or meters per second squared, I think, and it will do the right thing to make sure that the register gets set up accordingly. The last thing to do is basically to declare a backend API struct, give it references to both of those two functions, and then we register it in the emul dt_inst_define macro. So the generic emul struct that exists in Zephyr actually has a void pointer for a backend API already included. And you can set that with the last parameter in that macro, which is almost always null, because people haven't been using this before. But we'll take advantage of it. So that's all the work that we need to do over on the emulator side to basically get it ready for a generic test. So if you were adding this functionality to a new emulator, you could stop there, actually. The rest of this is just to talk about how the generic test itself is implemented so we can get familiar with how it operates. And so Generic test is live today, as I mentioned, and it's part of the sensor build all test. So this is a particular unit test that lives inside Zephyr that has a device tree associated with it that lists all the different sensors that Zephyr supports, categorized by what type of bus they're on. And so this is a really convenient place to start because it is the expectation that any new sensor driver gets registered here already. So we can basically use device tree macros to iterate through that list of sensors. And every time we reach one, we could basically declare a new z-test test function for that device. We get the device pointer automatically filled in. And we can call this run generic test function, which actually carries out the test. And we are repeating this for every single sensor that we know about. But the first check in the run generic test function is whether or not there is actually an emulator and the backend API associated with it. If it's not, then we're going to skip that test. Basically, it's hard to detect just from the device tree macros alone whether or not a sensor supports this. But this also provides some useful test collateral because you can basically see in your output all the tests on all the sensors that don't have support, so you can use that to kind of target which devices we want to work on. One of the other benefits of this build all test is actually now a run all test, I should say. Since we actually are initializing Zephyr, it will go through and run the init function at least on all of these drivers, which will at least test the initialization function of each driver, which does help a little bit. Sometimes that catches bugs on its own, but we are going past simply building, despite what the name implies. All right, so going a little bit further down in the generic test function, we're going to do that channel discovery routine that we mentioned earlier. So iterate through all the known channels. We're going to keep track of which ones the sensor emulator is actually able to support. We build out a table of channels and ranges. And then the final step that we do at the bottom right there is do that interpolation. So we create a set of test values that we can work with. And once we have those, we can start setting them on the emulator. So the key function here is emul sensor backend set channel. That calls into that API that we defined earlier. We give it the value. We give it the channel. Emulator goes off and does the right thing. We will then go ahead and read those values back from the driver, which is then, of course, talking through the emulator. And we capture all of those into our table. And then we can finally do a comparison at the end to make sure that we got back what we expected. So the first thing that we're actually going to do in this case is unshift everything. So one of the consequences of fixed point numbers is that if your decimal point is actually not in the same spot between two numbers, you cannot directly compare those or do arithmetic on them because the bits mean different things. So we basically just take that whole problem out by unshifting everything. It fills an N64 container in this case, but that doesn't matter. We're running on PCs here. That's actually the native size. So once we've unshifted the actual, the expected, and the allowed error, the epsilon value, we just use the z-assert within macro right here to see if we are in tolerance. If not, we can report an error to the user. Otherwise, we can just continue in the loop, testing all the other sets of values, and eventually moving on to other sensors. All right, so in conclusion, if you can write a backend API plus emulator for a sensor, you basically get a free test. Obviously, this will not be able to test every single feature of your sensor driver, but it does cover the data path, which I think is one of the most important things to focus on. And you can always still write a dedicated unit test for that sensor on the side where you work sensor-specific features. And so my ask for you guys today is that if there is a particular sensor in Zephyr that is important to your product or project, consider taking some time out of your day to contribute an emulator and backend API implementation for it. It does not actually take as much time as you may be fearing. I would estimate maybe like half to 1 day if you are generally well versed with Zephyr. And even if you think you've got a perfect driver that you wrote, you never know, it could be somebody else's PR down the road that introduces a regression into it. And if there's not testing going on to catch situations like that, then that is the vulnerability that we don't want to accidentally have happen. But the best recommendation I have would be to try to, every time you develop a new driver for a sensor, do the emulator alongside while it's fresh in your head. That's kind of the easiest time to just crank that out. So as promised, at the end I have a couple of references. So these are all various PRs that are associated with the generic test and the backend emulator API project. At the very bottom here is a reference to another talk from last year's conference about the sensors v2 thing, if you want to learn a little bit more about that. Yeah, so feel free to take a picture or download the slides from the web. I'll leave that up for a little bit longer, but aside from that, we can go ahead and enter the Q&A session. So yeah, do we have any questions from the audience?
Thank you. Does the emulator backend have an interrupt emulator as well, so you can do things like triggering and that kind of stuff? Or just registers on the I2C bus or that kind of thing?
Yeah, so right now it's just register-based one-off reads. But since we are tying into the the sensor v2 API right here, that does open up possibilities for that kind of asynchronous sensor reads that are often triggered by interrupts. So I think there's potential to work on that there. Okay. If it's like really particular to a certain sensor, then that might be a case where you do need to, unfortunately, write a dedicated unit test for that driver, though.
Okay, thanks. Also, I hadn't seen sensors v2 before. Is there a reason that the 32-bit and the 8-bit are separate and not in a structure like they were for v1 with the integer and fraction? Or is it just they decided to do it that way because they decided to do it that way?
Yeah, so the main benefit of having the single fixed point value is that arithmetic gets a lot easier. So you can actually add, as long as the shift value is identical, you can actually add and subtract those together and do multiplication on them. The previous implementation where you had the sensor value struct, where it had basically two numbers in one, made that pretty complicated because basically the first thing everybody would do would be to somehow recombine those two values. Yeah, so they would multiply, the first number by 1,000,000, then add the micro units into it or something like that, which could overflow or maybe isn't actually suitable for the application. So there is, of course, more of a learning curve to the Q31 numbers, but I do think it's possible to get used to it, and I think it's an overall improvement.
Oh, no, I understand that. I was just wondering why the 32 and the 8 are two separate things being passed in and out rather than just
okay. So you're saying could those be within one struct?
Yeah.
I'm sure they could be.
Just wondered if there was a reason that it was done that way, that's all.
It might be for compatibility with the DSP layer.
Yes, so Keith's comments is it might be for compatibility with the DSP layer. Yeah, I think a lot of this was designed with that in mind, so that could definitely be the explanation.
Okay, that makes sense. Thank you.
Just a note on that question, it could possibly be due to array support. If you have an array of 16 samples, you don't need the shift value repeated 16 times.
Yeah, so you're saying whether or not you could have a whole buffer of samples that are described by one shift parameter? Yeah, so actually in the Sensors v2 system, when you are doing like larger batched reads, the shift value is only sent once, and then you'll have a whole buffer of samples. For the emulator API right now, we're really only supporting just one-off samples, so this is just a simpler way to do it. But I definitely do see potential to expand this in the future to basically set up like maybe a whole waveform on the emulator so that when you do multiple reads in a row, it just returns one after another, and then you could use that to characterize a filter or something like that.
Thank you for the presentation. Well, one of the things you mentioned before actually explaining how the emulator worked and stuff was about a bug that, for instance, you have a driver or a sensor that it's working over I2C, that it's not working over SPI. Mm-hmm. So kind of like, I'm curious, how would this emulator detect those kind of problems?
Yeah, so that one was actually caught when we turned the build all test into a run all test. Because then it started initializing all those sensors, and that's when we started seeing some problems with some of them. So in that case, there was not an emulator involved, but it did shine some more light on and run some more code than we had been in the past.
Any other questions for Tristan? Oh.
Thank you. So I kept thinking about that epsilon and padding it a little bit, and I was wondering if you considered in the emulator API to get back not only the epsilon, but maybe Q31 type that the API will calculate as this is what I should have after losing precision, and use that as well for the exact comparison, not to get into well, actually use them together with epsilon as a double check, because that last bit sometimes can be important, because if the driver is truncating the last bit, that is actually noise. So I was wondering if that could be an option.
Yeah, that's a good point. So basically saying pre-compute what the actual value should be, just so that if there are regressions along the path that maybe even minorly affect the accuracy, that those can get caught.
Yes.
Yeah, I think that's a good idea, actually.
Okay, thank you.
All right, any final questions? All right, well, thank you so much for attending. It was nice talking with all of you. And hopefully I can review some drivers and emulators from you guys.